Hi there. Welcome to this special episode of 5-Minute Physics. This, in my wallet, as some of you know who've read my book, is a graph I have. Whenever I meet someone who says they don't believe in the Big Bang, I just take this out and say, see, the Big Bang really happened. And I thought I'd spend a few minutes today telling you why I can say that, because it relates to something I talked about in my history of the first 5 minutes of the universe in the last episode. And I thought, well, I can do better than that. I can actually show you how to calculate, basically how to cook a universe. I think Carl Sagan once said that if you want to know how to cook a chicken or something, the recipe for it, first start with the universe. And that's true of what we do when we look at the universe now. We see stars and galaxies, we see people made of the elements we're made of. And we can ask, how were they cooked in the early universe? This process is called nucleosynthesis. And we can calculate it. And it's one of the most fundamental predictions of the Big Bang. We start with neutrons and protons, which I told you before, that once the temperature of the universe falls below the mass of the neutron and proton, they're basically the only particles around, plus electrons and neutrinos. All the quarks and everything have combined into neutrons and protons. There are no elements yet. There's just neutrons, protons, electrons, neutrinos, and radiation. And there are a lot of reactions taking place. It's very hot and very dense. This is a time when the universe was less than a second old. And neutrons plus neutrinos go to protons plus electrons. Neutrons plus positrons go to protons plus neutrinos. And it goes backwards the other way as well. Electrons hit new protons and form neutrinos plus neutrons, and antineutrinos plus protons form neutrons plus electrons. So all of these collisions are happening, and all of these processes are taking place. But as the universe cools, something important is necessary to understand, and that's that the neutron is more massive than the proton. The mass difference is 1.29 million electron volts, which is about 1/1000th of the mass of the neutron and proton themselves. So the mass difference is very small. But when the temperature falls below an energy associated with 1.29 million electron volts, then it's hard for an electron and a proton to form a neutron because they don't have enough energy to create that much mass. And so once the temperature falls below this threshold, the process starts going in only one direction. Neutrons turn into protons, but protons don't really turn into neutrons. So what happens at a temperature below this temperature is the number of neutrons over the number of protons begins to fall exponentially. It falls exponentially as e to the minus q, this mass difference, over the temperature at the time. If the temperature is very large, then this number is very small, and e to the minus a small number is 1, and so this number is 1. But once t starts falling below q, this number becomes significant, and the number of neutrons starts falling exponentially. And the number of neutrons would fall exponentially forever, and it would basically go to 0 if something else didn't happen. But at a temperature about 0.7 MeV, something happened. At that temperature, the universe has expanded enough, so now the particles are separated enough so that a neutron can't find a neutrino to turn into a proton plus an electron, or a positron. And so the process has already stopped going in that direction, but now at that temperature, it stops going in this direction. That's what we call the freeze-out temperature. And that means after that point, this neutron to proton ratio is frozen in. It doesn't continue to fall because the reactions stop happening. And if you plug in about 0.7 MeV over 1.29 MeV and put the exponential in, you find out that this neutron to proton ratio is about 1/6. They're about 15%. Okay, so that's the number of neutrons that are baked into the early history of the universe, and that would be fine, except for the fact that we also know that neutrons are unstable. They have a lifetime of about 880 some odd seconds. So for later times in this, the number of neutrons is the initial number, 1/6, times e to the minus time over 885 seconds. And over later and later times, this number would continue to go down to 0. So all the neutrons would be gone if it weren't for another process. And that process involves nuclear reactions. Because neutrons can interact with protons, not to produce, and neutrons can interact with protons in another way than what I showed you before. They can combine together to bind into the nucleus of heavy hydrogen or deuterium. And this process can happen because it's what's called exothermic. It releases energy. So even it happens in principle at very low temperature. So the neutrons can combine with protons, and once they're in the nucleus of deuterium, they're stable. That's stable, and they release a photon in the process. So neutrons and protons begin to form deuterium, heavy hydrogen. But there's a problem. Heavy hydrogen is very weakly bound. So the process can go the other direction. Namely, a particle of radiation can interact with the nucleus of deuterium and break it apart. What's so-called photodissociation, break it apart into neutron and proton. So you don't begin to form much deuterium until the energy is low enough so that this reverse process doesn't break it apart. Now, until you form deuterium, you can't form any other heavier elements by any other nuclear reaction. So this is what we call the deuterium bottleneck. You don't form deuterium at high temperatures because the deuterium gets broken apart. But when the temperature is about 1/10 of an MeV, or the age of the universe is about 168 seconds, then it turns out you begin to form enough deuterium, this other process is suppressed enough, so that deuterium can find another deuterium and collide together to form the nucleus of tritium, a proton, a neutron, and also a proton. That is an unstable, heavy isotope of hydrogen. Or deuterium plus deuterium can form the nucleus of helium-3 with 2 protons and a neutron, releasing another neutron. And then deuterium plus helium-3 can go to form helium-4 and release a proton, or deuterium plus tritium can produce helium-4 plus a neutron. Now, helium-4 is stable and very heavily bound. So once this can happen, you basically immediately, all the neutrons that are still around in deuterium can go to form helium-4. So once this bottleneck is passed, basically helium-4 is produced right away. So we can calculate what the abundance of helium-4 that's produced is, because the number of neutrons over the number of protons at this time of 168 seconds is 1/6 times the exponential of minus 168 over 885, and that's about 1/7. So we can just do a little playing with algebra. The fraction of neutrons, the number of neutrons over the total number of neutrons plus the number of protons, can be easily calculated. That's the number of I divide both sides, top and bottom, by the number of protons, so that's the number of neutrons over number of protons, plus over number of neutrons over the number of protons, plus 1, and that's 1/7 over 8/7, and that's 1/8. So the fraction of the universe, the fraction of neutrons compared to the number of neutrons plus protons is 12.5%. But there's something else we know, that the number of neutrons is twice the number of helium atoms, because it takes 2 neutrons to be in helium. If all the neutrons that are left over are in helium, the number of neutrons is twice the number of helium atoms. So we can write this same fraction, xn, number of neutrons over number of neutrons plus number of protons, in a weird way. We can write it as twice the number of helium-4 atoms over twice the number of helium-4 atoms. What's the number of protons? Well, that's the total number of protons in the universe. That's the number of hydrogen atoms, nuclei, because nucleus of hydrogen is just a proton. But plus 2 times the number of helium atoms, because there are 2 protons in helium. Well, this is 2 plus 2, so that's 2 times the number of helium atoms over 4 times the number of helium atoms plus the number of hydrogen atoms. Why have I chosen to write it that way? Because we can ask, what's the fraction of helium by weight in the universe? Well, helium has a mass number 4. And if helium and hydrogen are the only things around, the fraction by weight is the weight of helium, 4 times the number of helium atoms, over the 4 times the number of helium atoms plus the number of hydrogen atoms. But this is twice that. So the fraction of helium by weight is twice 12.5% or 25%. It is therefore a generic prediction, plugging in these numbers based on the measured strength of nuclear reactions in the laboratory, that we should predict that about 25% of the universe is helium, and therefore about 75% of the universe is hydrogen. That's a generic prediction of what's called Big Bang nucleosynthesis. It first was done around the 1960s by people like Jim Peebles, who won the Nobel Prize this year. And it's a wonderful prediction because it basically is based on just measuring things in the laboratory, nuclear reaction rates, and saying, therefore, what's the abundance in the universe? And then we can try and measure it and compare predictions with observations. Now, you may say, why did the universe stop with helium? The answer is there are no stable nuclei with mass number 5 or 8. Now, in order to have collisions happening, remember you have, when you were making helium, you had neutrons, protons, and helium. Basically, that's all that's left after you make the helium, and the neutrons are gone. So you could maybe have a helium plus a proton make something else, helium plus a proton, but there's no nuclei that have stable mass number 5, which is what you'd get by taking helium plus a proton. The other thing you could do is bombard 2 helium atoms together to make something with mass number 8, but there's no stable nucleus with mass number 8. So the process essentially stopped there, almost. Now, there are some remnant abundances of 2 other things. Remember, deuterium was produced on the way to producing helium. Not all of the deuterium collides to produce helium. It's not 100% efficient. And you can show that basically 1 part in 100,000 of the deuteriums that were initially, of the neutrons that were initially produced went into deuterium that didn't collide to form hydrogen. So the predicted abundance of deuterium is about 1 part in 100,000. Now, there is a little bit, the next lightest element is lithium with 3 protons in it. And some complicated processes that I won't go into produce a very small amount of lithium, about 1 part in 10 to the 10th of the universe. So what do we predict? We predict that roughly 25% of the universe would be helium by weight, and by number, 1 part in 100,000 should be deuterium, and 1 part in 10 billion should be lithium. What makes this amazing is that our predictions vary over 10 orders of magnitude. And then we ask astronomers to go out and try and estimate what the actual primordial abundance of these elements was. And it took a long time to do that. There's a lot of uncertainties. You have to look at old systems that haven't been processed in stars. But guess what? Roughly 25% of the universe is helium. Roughly 1 part in 100,000 of the universe is deuterium. And again, from looking at old stars, roughly 1 part in 10 to the 10th of the universe is lithium. So this prediction, which varies by 10 orders of magnitude, agrees with observations. But you can actually even do better than that, because now we can actually do something else. Because the fact that this agrees with observation allows us to measure something else. Because if I have an omelet and I have 3 eggs, I make a bigger omelet than if I have 2 eggs. And clearly, if I look at this prediction versus the number of neutrons plus the number of protons, if I start out with a universe that has more neutrons and protons in it, I'll produce more helium-4. But in fact, if I have more neutrons and protons, then the reactions that produce helium-4 will be more efficient, and I'll have less leftover deuterium. So if I plot this as a function of this total number density of neutrons and protons, it'll go up. The helium-4 prediction will go up with this number. The deuterium prediction will go down. And that means if I can compare this with observations, I get a prediction for the total number density of neutrons and protons. And that's how we know how many neutrons or protons are in the universe today. Now, you might say, why should I believe this? Because there's an independent way of measuring the number of neutrons and protons in the universe. It turns out, if we look out at the cosmic microwave background, which is radiation coming at us from the Big Bang, it's almost completely uniform, except for some hot spots and cold spots. And where those hot spots and cold spots come from is that the radiation was emitted or scattered from large clumps of matter that was collapsing just at the time the universe became transparent to that radiation and it came to us. Now, if I have more neutrons and protons and electrons in particular, because the photons are scattering off electrons, and the number of electrons is equal to the number of protons because the universe is neutral, that the greater the number of electrons, the bigger will be the disturbance of this microwave background radiation. And by measuring the amplitude of those temperature fluctuations, we can determine the number density of electrons at the time the cosmic microwave background was created. And guess what? Bang on with the prediction that you get by measuring the light element abundances. And that means, independently, we now not only know the number density of neutrons and protons in the universe, the total amount of normal matter, because all normal matter is made of this stuff, But we also know that the prediction of the Big Bang, based on just measuring things in the laboratory, and for which there are no dials that you can twiddle, over 10 orders of magnitude predicts exactly what we see. So we know the Big Bang actually happened because the predictions agree precisely with the observations that could be done independently. By the way, this is also how we know dark matter is not made of normal matter, because this tells us what the number density of neutrons and protons is, and therefore we can actually measure the amount of mass in the universe by weighing galaxies, and we find it's 5 to 10 times bigger, and therefore that material can't be made of neutrons and protons or normal matter. So we know dark matter is made of something else. So that's why when someone comes up to me and says they don't believe in the Big Bang, I show them this picture. And there's the agreement. Here are the predictions. There's helium-4 and deuterium, and also helium-3 and lithium. And this is a number that but from observations of the abundance of light elements, and also from the cosmic microwave background. And the predictions are bang on with the observations. We know the Big Bang really happened. One of the most remarkable and exciting calculations you can do in cosmology, because it tells us we understand the universe back to about 1 second in its history, which is remarkable. So the last thing I want to say is that, by the way, you may be disappointed that the universe only created hydrogen, helium, and a little bit of lithium, because you're made of carbon, nitrogen, oxygen, and iron. And as any of you who followed me know, I've said many times, the only place those things are created, once the universe these things were created when the universe was about 5 minutes old, that was it for almost 1 billion years, until the first stars were formed. And those stars created all the heavy elements by nuclear reactions in the stars, carbon, nitrogen, oxygen, and iron. And the only way they could get into your body, as I've often said, is if the stars were kind enough to die so that we could exist. Because when those stars explode, that material is spewed into the galaxies, so other stars form and planets around them. And all of the carbon, nitrogen, oxygen, iron, all in your body has been inside at least one star that's exploded. You are a star child. And I said before, that in my mind is one of the most poetic things I know about nature. So Big Bang nucleosynthesis tells us not only that the Big Bang really happened, but that we are connected to the universe. We are stardust, and it's a lovely thing. Thanks.